In this video, we'll look at how to solve an equation in which you have one absolute value equal to another, similar to what we have here in this equation. The absolute value of ax plus b equals the absolute value of cx plus d. When we think about this scenario, it might be a little easier if I just say I've got the absolute value of something on the left equal to the absolute value of something on the right. Okay. What we have to think are all of the possibilities for the signs that this left side could be versus the right side. Really, either the left is positive or it's negative, and same thing with the right. The right is either positive or negative. The absolute values, in essence, eliminate the signs, so they could be equal even though they could be either of these signs on each side. So let's look at the four options. If the left is positive, that could be equal to a positive right. If the left is negative, that could be equal to a positive right, because, or if the left is positive, it could be equal to a negative right, or if the left is negative, it could be equal to a negative right. These are the four options if you look at combining whether the left is positive or negative and whether the right is positive or negative. Remember, the absolute value eliminates the signs, so when we undo the elimination of the signs, these are the four options we have. Luckily, even though this seems complicated, pairs of these operations really, or these options, are really the same thing. If you think about the left equal to the right, but they're both positive, it's actually the same thing as having a negative left equal to a negative right, because you could simply divide this setting down here by a -1, and it would take you back to a positive left equals a positive right. What this means is that one option for solving an absolute value equals an absolute value is just to remove the absolute values. Ax plus b equals cx plus d. Just remove them, solve, and you get one solution. If we look at the other two options, a negative left equal to a right and a left equal to a negative right, once again, these actually mimic each other. And the reason is that you could divide by a -1 in this first one, and you'd get back to a left equal a negative right. So what we do for an alternative, the other alternative option that would take into account all aspects of what could happen, is we could set the left side of the equation equal to the negation of the left side. So if you do this and solve, you will have the other solution that could come up from solving the absolute value of ax plus b equal to the absolute value of cx plus d. The explanation here, it may seem complicated, but in essence, we are still doing something very similar to what we did, which is the inside of the left side is equal to the positive of the right side, or the inside of the left is equal to the negation of the right. And that's pretty much what we were doing before. There's just, because there's expressions in each one of them, you have to remember to distribute the negative in the second case. All right, so let's look at some specific examples. We've gone over the theory, but some specific examples will help you pinpoint it. So let's solve the equation. The absolute value of 5x plus 7 equals the absolute value of 4x plus 3. Using the explanation before, remember we're going to split this into two equations, one of which is just eliminating the absolute value. There you have it. And the second one will be negating one side. So 5x plus 7 equals negative 4x plus 3. So you want to negate one side, not both sides, just one side. So if we solve these equations, subtracting the 4x from both sides, we get x plus 7 equals 3. And then subtract the 7, x equals -4. That would be one solution. And over here on the right, first we need to distribute the negative. Then we'll add 4x to both sides. We're going to move this over. So we get 9x plus 7 equals -3. Subtract the 7 from both sides. 9x equals -10. And divide by the 9, -10/9. So we get two solutions. We should check those. So if I put in the -4 as my first check, the absolute value of 5 times -4 plus 7 should be equal to 4 times -4 plus 3. Let's see what happens. So calculate the left side, we have -20 plus 7, and that would be the absolute value of -13, which is 13. Looks good so far, but let's calculate the other side. The absolute value of -16 plus 3 is the absolute value of -13, which is 13. That checks. Second check, the absolute value of 5 times -10/9 plus 7 should be equal to the absolute value of 4 times -10/9 plus 3. Let's check this out. So remember, when multiplying fractions, you multiply top and bottom. So -50 over 9. Now to add the 7, we're going to need a common denominator. Currently that's 7 over 1. So or the denominator is 1. So we will go ahead and change that denominator to 9. So the 7 is going to become a 63. We'll finish calculating, doing the next side. -40 over 9 plus 3. I am going to need this to become a common denominator, so that 3, it would be better if it became a 27 over 9. 27 over 9 is 3. So, continuing on, positive 13 over 9 is equal to -13 over 9. And I'm running out of room here, but the absolute value of 13/9 will be 13/9, and the absolute value of -13/9 will be 13/9. So you do get this checking just like in the first one. So we do get two solutions here. So the solution set contains these two values, -4 and -10/9. Let's look at another one. All right, so let's graph this equation to find our solution. Now remember, we want to graph each side. Y equals the absolute value, ABS for short, of 5x plus 7. So there's our first side, our left side. Our right side will be y equals absolute value of 4x plus 3. So we can actually see that they definitely cross here. That would be at -1.11111. If you look at that 0.1111, that's actually 1/9. So if you think back to the answer we got in the previous example, which is this same equation, we got -10/9, which is -1 and 1/9. So here we have -1, and 0.111 is really 1/9. So there's one solution. Let's zoom out here, and I think we get another solution up here at -413. So the second solution is -413, and the first one was that -1.111, which is -1 and 1/9. So those solutions match exactly what we got when we solved this algebraically. Here's another example where we have an absolute value equal to an absolute value in an equation. Once again, to solve this, we're going to split this into two separate equations. The first where we simply drop the absolute values and solve. The second where we drop the absolute values, but we negate one of the sides to represent that one of these two insides could be the opposite sign of the other. So in this first left side here, we're saying that they have the same side, and this right side, we're saying they have opposite signs. When we go to solve this, if we subtract x from both sides, we get a false statement. So that's saying there's no solution from this first statement. But over here, if we negate the x and negate the 6, and then move the x's to the same side, we get 2x minus 9 equals -6. Add the 9 to both sides, we get 3. 2x equals 3, divide out the 2, and we get 3/2. So on this side where we thought of both of these insides as being the same value, or the same sign rather, we actually get no solution. But when we think about them as opposite values, we actually can get a solution of x equals 3/2. Let's check that real quick by graphing. So instead of me checking algebraically, let's practice looking at what's happening graphically here. But if I've done this right, I should have the solution of 3/2. Let's check it. So to solve graphically, we'll enter in the two sides of this equation. Remember, one side, the left side, was y equals the absolute value of x minus 9. The second side, the right side rather, was x absolute value of x plus 6. So we get two V-shaped graphs here, and we can definitely see one intersection right there at point 1.5, which matches the solution we got earlier, because remember the solution we got was 3/2. So that matches. And if you keep looking, even no matter how far you zoom out, what you see is that the edges of these graphs are always parallel to each other. So you aren't going to have these V's cross in any other place except for this one spot down here, right there at 1.5, 7.5. So the only solution to this equation, x minus 9, or the absolute value of x minus 9 equals the absolute value of x plus 6, is 3/2 or 1.5. Let's look at one more example of this. Here we have the absolute value of n minus 3 equals the absolute value of 3 minus n. Once again, we want to either think about both of these as having the same sign, so n minus 3 equals 3 minus n, or remember the absolute value can make it look, even though they have opposite signs, make it look like they have the same sign. So if we think about them as opposite signs, we would negate one of those two sides. So where we think about them as the same side, we would want to get n's on one side, so add n to both sides, and then add the 3, and we get, when we divide by 2, we get 3 as a result. Over here, when we think about them as opposite signs, n minus 3 equals negative 3 plus n, so we're negating by distributing the negative. Then when we subtract n from both sides, we get negative 3 equals negative 3, which it's actually a true statement. And as such, that means that potentially all real numbers are solutions, because this is true for every n. So this is an interesting result. What this is saying is that potentially if n is equal to 3 and then all real numbers are solutions, really I don't have to say n is equal to 3 if all real numbers are solutions. We can actually just say all real numbers are solutions. Let's see what is happening in the graph to see it in terms of this making sense. So let's, on the next screen, look at the graphical relationship of what's going on here. All right, here we go. Let's graph the left side, let's graph the right side, and see what happens. So our first equation for the left side is the absolute value of, now we usually use x here because Desmos understands x is the input, y is the output. So instead of using n, we'll use x minus 3. So there's our first graph. And when we plug in the second side, y equals the absolute value of 3 minus x, what you see is that our new green graph is right over top of the blue one. And I can toggle back and forth and turn these off. So if I don't have the blue one on, if I put the blue one back on, actually, let me try this with the green. If I take the green off, you see the blue graph. Put the green graph back on, you don't see the blue graph anymore because green graph is right over top of it. So these two graphs are exactly the same, and that's why you end up with all real numbers as solutions. So this is an interesting scenario in that what we've seen is that we could potentially have one solution, two solutions, or all real numbers as solutions, or even no solutions in an absolute value equation.